The next talk is on constraints on primordial non-Gaussianity with Planck, and will be presented by Sabino Matarrese from the University of Padua.
Okay, so my talk is, of course, quite connected to the previous one. It's just a different view of the presence of non-Gaussianity in the data. Our goal, in a sense, it's much easier because we have a very targeted problem, which is to look for specific forms of non-Gaussianity and to see whether these forms of non-Gaussianity are there or not. Okay. During the last, I would say, 15 years, more or less, non-Gaussianity showed to be a new route to falsify inflation. In the 80s, people were looking at strong amplitudes of non-Gaussianity as possible alternatives to the standard hierarchical galaxy formation mechanism. But then later on, the quality of the data implied that the constraints became stronger and stronger. And because of that, there was a new era with the so-called FNL models from inflation, which were proposed more or less in the 90s. And in the course of time, what happened was that this new parameter FNL became very rich in terms of model proposals and possibility to constrain variety of different models, so it became a sort of new parameter of cosmology. So primordial non-Gaussianity emerges as a sort of new smoking gun on standard inflation models, or more in general inflation models, which complements the search for primordial gravitational waves through B modes. Okay. The simple form of non-Gaussianity which has been proposed many years ago is such that the quantity phi, which roughly speaking is called gravitational potential. More precisely, it is defined by 3/5 times the common curvature perturbation on super-horizon scales. Can be written as a sum of a linear Gaussian potential plus FNL times phi linear squared plus GNL times phi linear cube, etc. In the most general case, these quantities FNL and GNL, instead of being parameters, are functions. Okay, but that idea simplifies a lot our search for non-Gaussianity. At the beginning, it was only a phenomenological approach, but later on, it proved to be a very rich way of quantifying the predictions of inflation. So during the course of maybe the last 10 years, there were a huge number of models which were proposed, which gave a meaning to these quantities FNL and GNL. Okay, roughly speaking, the amount of non-Gaussianity, percent of non-Gaussianity which you have in the data is something like 10 to the minus 5 times FNL or 10 to the minus 10 times GNL, and then you put your numbers and you get the precision by which you can constrain non-Gaussianity in the data. Okay. The scientific target of the Planck project 24 was that of constraining with high precision and/or detect primordial non-Gaussianity as due to, let's call it non-standard inflation, and look for the non-Gaussianity amplitude and shape, which measure deviation from standard inflation, perturbation generating processes after inflation, initial state before inflation, etc. Okay, we do test some specific forms of shapes of non-Gaussianity, local, equilateral, orthogonal, and many more shapes than that. And we also constrain one of the quantities which characterize the primordial trispectrum, which is so-called parameter tau NL, which in the case of single field inflation is a number times, in the case of simplest local models of inflation is a number times FNS squared. Sorry. Okay. Let me define the main quantity that we use in our analysis, which is the angular bispectrum that's GMB, BL1, L2, L3, M1, M2, M3, which is just the product of 3 ALMs. That can be written in terms of an integral, which is called the Gaunt integral, times the so-called reduced bispectrum BL1, L2, L3. This reduced bispectrum has to satisfy a number of symmetry conditions, which are written there, which implies that it has to these triplets, the number quantified by these triplets has to be in that shadow part on the diagram, which was called a tetrapid, which is a tetrahedron with a maximum L, which is, of course, the resolution of your experiment. Okay, so each point in the shadowed area is a value of BL1, L2, L3. Okay. As I told you, originally this FNL was just a number, okay, which is what we now call the local non-gaussianity. Later on, people proposed many more shapes, the so-called equilateral shape, which is very obvious to understand, the so-called folded shape, but many, many more, as I'm going to sketch a little bit in the rest of my talk. Let me give you, in the plot which I showed you before, the way in which these shapes appear. Okay? So the local shape has been shown to be maximal for the so-called squeeze configuration. So it is maximal in the corners of that tetrapid. The equilateral shape, of course, is in the diagonal. Okay? The orthogonal shape is more difficult, is less intuitive. It's shown in this part of in this plot here. This is another shape which happens to be real. Okay, we do detect it in the data, and it is due to the so-called ISW lensing effect. Okay, in all these shapes, you do see some oscillations. Okay, these oscillations in the real data, as we will see, come from the fact that we basically see cosmic variance, and the cosmic variance is, of course, relative to the power spectrum itself, which has acoustic oscillations. Okay. By spectrum shapes, as Francois already mentioned before, different shapes refer to different models of inflation. The local shape is typical of multi-field models, like the Carbaton, equirautic cyclic models, etc. The equilateral shape is approximate what you have in some single-field models, typically with non-standard kinetic terms, higher derivative operator, etc. The orthogonal shape is defined like that because it is orthogonal to the equilateral shape. Is also present in, for instance, in the effective field theory of inflation. The flat shape occurs typically when you have excited initial states at the beginning of inflation, but is actually more general than that. And there are many more shapes than that. Okay, so trying to fit the bispectrum is something which is extremely complicated. So people invented techniques, more compact techniques, which allow to obtain numbers from the data. And typically people try to compress the information in, let's say, the quantity FNL. Okay? So the idea is to get an optimal FNL bispectrum estimator. At lowest order, the optimal bispectrum estimator is given by this expression here, which has been obtained by a number of people. It is a modification of the so-called KSW estimator with some a more complicated weights, which have been shown to be the optimal weights for the analysis. And there's also a linear term which is necessary whenever you break rotational symmetry. The important point, however, is that this form doesn't tell you necessarily what you have to do in practice. You still have freedom of deciding which basis you want to use. Okay? When we started our analysis, we thought to apply different techniques to look for FNL. Okay, we realized during the years that this idea of using different techniques was extremely efficient, and that these different techniques were actually different forms of the same underlying optimal FNL estimator. Okay, so we use at least 3 of them: the KSW technique in this extended form, plus an extension of this, which is called SQCL, which has been proposed by Mushi and Evans. SQCL is basically a quantity which depends upon L, which implies that instead of detecting a single number, if you detect it, you get a function, and because of the form of this function, you have a better control of whether what you see in the data is the quantity that was predicted by the theory. A second possibility is so-called beam by spectrum, which was proposed by Martin Bucher, Martin van Tent, and Carvalho in 2009. This the estimator, the results of the estimator will be detailed will be presented in more detail by Martin van Tent on Thursday. The idea of the beam by spectrum is quite easy to understand. You basically beam in airspace your by spectrum. Okay. A third technique is the so-called model expansion, which was proposed by Ferguson, Liguori, and Shellard. Michele Liguori and Paul Shellard will present different aspects of this estimator still on Thursday morning, basically. And the idea here is that whenever you have a bispectrum which is not separable into quantities, into products of quantities which depend upon individual upon L1, L2, L3, you try to express your true bispectrum, your model bispectrum, in terms of superpositions of modes. Okay, you need many different modes in many cases. In the practical implementation of this technique, we used around 600 modes to get convergence to the required shapes. In the case of beam by spectrum, we used 51 beams in order to once again to get convergence. Besides these techniques, we also applied a couple of suboptimal estimators. One is the wavelet decomposition, which in principle is also optimal, but implementation is not yet as optimal as required by the data. And the Minkowski functionals, which are a completely different technique, which is not required to be optimal, actually, but it's very important because it is totally independent from the others. This will also be mentioned by Ben van den in his talk. Ben will talk a lot about the massive validation campaign that we used to compare the estimators, to compare the result of estimators with Gaussian and non-Gaussian simulations, and to compare the estimators with Planck data in different forms. Okay. Okay. The first important result that we get, I think, will also be mentioned by Karim Ben-Abed in his talk about the lensing in the SW part, is a clear detection, a 2.6 detection of the so-called ISW lensing by spectrum. Many papers during the last 5 years have looked at possible contaminants of primordial non-Gaussianity. It turns out that apparently the only important contribution comes from this coupling of integrated subgroup and the lensing contribution. There will be a poster by Anna Mangili on this specific result. But let me just tell you that we do see this effect in this plot here, okay? And also this QCL plot shows you that we do detect this effect here, okay? So this is the amplitude of the signal, and this is the bias that we compute, and we have to subtract from the FNL results in order to get primordial ones. Okay, we also detect Poissonian point source contribution, which is very important in order to be taken into account when arriving to the primordial contribution. And then let me go to one of the most important results. Local, equilateral, and orthogonal. Here I only show the KSW result for the SMICA map, but we have this result for the 3 estimators, also for the 2 suboptimal ones, and for the 4 component separation techniques. In the local case, the difference between different component separation techniques is about 1/6 of the error bar. In the equilateral orthogonal, it is a bit larger, but still much smaller than the standard deviation. So for the local case, we get 2.7 plus or minus 5.8 after marginalizing over the point sources by spectrum contribution and subtracting the SW lensing bias. Okay, for the equilateral, we get once again, a number which is consistent with 0, and for the orthogonal, we also get a number which is very, very well consistent with 0. Okay. Ben will also talk about validation on simulation Planck data of these results. We used, sorry, this should be 73, not 72. We use the union mask U73, and we apply a diffusive in painting pre-filtering procedure to the data in order to get these results. Okay, this is the plot, the general table which I was just mentioning before, which shows you the result for all the comprehensive ratio techniques and all the optimal methods. This plot is also quite interesting because it shows you the difference between different estimators, okay, for local, equilateral, orthogonal, ISW lensing part, and for the 4 component separation technique, and you do see the excellent agreement between these different techniques. Okay, this is one of the 2 reconstructions that we make of the primordial bispectrum. This is shown in terms of the so-called modal decomposition technique for different component separations. In the corners here, you could see the ISW lensing contribution. Once again, the very fact you see these changes of colors is the evidence that the inherent cosmic variance is showing up the underlying Doppler peaks. Okay. The same with the so-called beam by spectrum estimator. This will be much better shown in terms of a movie, which I'm sure Bartian will show you on Thursday. Otherwise, it's difficult to understand what is in this data. Anyway, these plots are the data divided by the standard deviation for a fixed value of L3 as a function of L1, L2. Okay, it can be shown for different L3, of course, but in a movie you can see much better the flow of information. Okay, here are the results for these suboptimal techniques. They are still consistent, fully consistent with the result of the optimal estimators, even though, of course, the error bars are larger, but we do have perfect consistent with the previous results. Besides looking at these 3 fundamental shapes, we looked at a bunch of different models, more exotic models, we call them, okay? Implied by, for instance, by non-Paris vacuum, resonant models, etc., etc. Okay? I'm pretty sure that Paul Scheller will tell you about these results, so I skip this part. Let me also only mention the fact that in this list of different models, we do find something interesting that was also pointed out by Francois earlier on. For instance, in this particular case, after subtracting the ISW lensing contribution, we get something which is 2.2 away from 0, for 2.2 sigma away from 0, if it means anything. It's something interesting which has to be studied further, and it's just one of the many possibilities that you can have different, at looking at different models. Another thing that we did was to try to get the first constraint on the trispectrum. That was done only for the so-called tau and L parameter, which is very interesting for consistency in multi-feed models. And we get a bound which is less than 2800, which is roughly 1 order of magnitude better than the previous bound from WMAP. Okay, conclusions. We have detected the integrated subsurface lensing by spectrum as expected in the lambda CDM scenario, that is with an amplitude as expected in lambda CDM scenario. We have the right constraints on linear scenarios that generate primordial Gaussianity, including general single field models of inflation inside initial states and directional independent vector models. We have provided an initial survey of scale-dependent feature and resonance models. These results bound both general single field and multi-field model parameter ranges, such as the speed of sound, which has to be larger than 0.02, and the Carverton decay fraction, which has to be larger than 0.15, only in terms of FNL. So it's a bound which is different from the one you obtain using isoconversion modes. We have constrained the amplitude of the 4-point function, the local model, to be less than 2800. The simplest inflation models are favored by Planck data. Okay? Multi-field models are not ruled out, but also not detected. Equilateral cyclic models are either ruled out or under severe pressure. Taken together, these constraints represent the highest precision tests to date of physical mechanisms for the origin of cosmic structure. Prospects for the future. Short term, improve FNL limits with polarization and full data. Look for more non-Gaussian shapes, scale dependence, etc. Constrain GNL. Long-term goals, reconstruct inflationary action. Are models with large GNL and small FNL preferred by laws of nature? That's an important physical question that we can ask. If quadratic non-Gaussian turns out to be small for all shapes, which is obviously a question mark, we can go on and search for FNL of order 1, nonlinear relativistic effects, and second-order radiation transfer function contributions, which is very challenging, of course, and requires a set of data, basically. What about being even more ambitious and looking for FNL over 10 to the minus 2, which is the tradition for standard inflation? The future is very likely in terms of CMV polarization plus relative structure plus 21 centimeter background and whatever you can have in mind is this direction.
Thank you. Questions? Just one or two questions. All very clear. Okay. Yeah, there's one there.
There is a question there.
Yeah.
About how
Wait a second, please.
So about the upper bound on tau NL, so you give only upper bound on it, but it can also be negative, I think. So could you have some, so do you have some idea about its lower bound on it?
On what, sorry, on?
About tau NL?
Sorry, I didn't understand that. About tau NL. Okay, this is not an upper bound on the absolute value. This is an upper bound altogether. That's it. Yeah, I just say that it's an upper bound altogether. It's not on the absolute value. It's an upper bound.
Lower bound.
Okay, thank you.
We don't have a lower bound.
Any other question? So, yeah.
Sorry, I'm thinking about that. Of course, tau NL has to be larger than FNL squared in most multi-field models. So basically, there is no interest in looking for negative values. Yeah. I was just thinking about that. I mean, there is no interest in looking for negative values because it has to be larger than FNL squared times 25 divided by 36. Okay.
Sabino, I have a question for the very far future.
Mm-hmm.
Do you think that the fourth generation CMB mission could be able to measure FNL of the order of 10 to the minus 2?
CMB only not. But the idea is that you should combine together different measurements. Unfortunately, for the CMB, we know that an ideal experiment cannot get values smaller than for the local case 3 or something like that. You can improve by polarization, but there is an upper bound, which is a lower bound, which is quite large. Okay, but you can use different data sets. For instance, 21 centimeter background can be extremely promising in this direction.
Okay, if there is no more questions, then let's thank again to Sabino and all the speakers that this afternoon. And, we will reconvene at 4:35.
10-minute break, that's it.